So welcome back to this session after the coffee break. The different talks we have in this part is going to be about the future of energy, and it's going to be a roundtable. So we first are going to give a short presentation of the different people that is composing the roundtable, and then we are going to have a period of time so you can make questions and answers. So to start with, we have Sara Molinero. She's an engineer expert in regulation in energy. And after working in Naturgy, now she's working in Iberdrola since September 2022. And she is working on regulation of renewable energy and electrification. So the floor is yours.
Thank you very much. I would like also to add that I am a former student of Professor Cabellos and Professor Perlado, so it is a pleasure for me to be here. Thank you very much, and also for the invitation to Iberdrola to exchange some views with you. Well, I think most of you know Iberdrola, at least the European ones. I know there are also people from other jurisdictions. So I will tell you that Iberdrola is one of the largest companies worldwide. It has more than 40,000 megawatts of renewable energy, and it is committed to developing renewable energy, a smart grid, and large-scale storage so as to provide advanced solutions to our customers. So very much committed also to our end customers. Of course, Iberdrola supports efforts to move to a low-carbon economy, which is both environmentally and economically sustainable. So let's move to the presentation. I will present our views at how we see, the future, that it is full of uncertainties and challenges, and also opportunities. So when we look to the picture, it is clear that the European Union has committed to a neutral economy in 2050, and it has already set its target for 2030. These targets are pretty ambitious, probably you already know, which are like 55% reduction of greenhouse gas emissions, 42.5% of renewable energy in the energy mix, and 36% of energy efficiency increase. I think that it has been mentioned before, the current energy crisis shows that we need to progress faster on more renewable development, so that we are less dependent on gas and on fossil fuels. This also has an impact on our economies and and therefore the European Union is very much committed to increase and accelerate this renewable development. In Spain, of course, you know that these targets that are set at European level, they go with what we call a national energy and climate plan, that it is what each member state commits to develop at their national basis. So for Spain, it's called PNIEC in Spanish, but it's this national energy plan. We had a plan already approved in 2020, and this plan has been revised recently. It is only a draft. It was sent for a public consultation just before the summer. So what you have there is like the proposal of the Spanish government, but it has not been approved yet. In any case, what I would like to show you is that also the Spanish government is moving forward more ambitious, more commitment, more greenhouse gas reduction, greenhouse gas emission reduction, and more renewables. For the electricity sector, I think this is something really challenging, because the figure that we have already is that we would like our generation energy mix to be 74% based on renewables, and the new draft sets a target of 81% renewable energy in the generation mix. So of course this is a challenge, and this implies really to move forward and a massive movement on investment. You can have a look here how we were in 2020, how we are today in 2023. This is real data just from the system operator of October 23. And then you have there the last draft proposal. So what we have is that we will move from 74% of renewable energy, so this is power generation capacity installed, to 160 gigawatts. So plus 32 gigawatts of wind energy, plus 53 gigawatts of solar photovoltaic, and 15 gigawatts of storage new capacity. Unfortunately, nuclear is not the winning technology. According to the Spanish government, it is expected that according to the current information, nuclear power plants will close after their lifetime, and so they will be in 2030 4 gigawatts of less nuclear capacity in Spain, according to this provisional draft. So what does it mean? So the investment challenge is clear, and it also puts a lot of it means that we all need to accelerate. I will give you some figures so that you can understand this investment challenge. If we see the ratio of investment in wind energy in Spain, the highest investment ratio per year was 2,200 more or less megawatts per year. And now we have to move, if we take these 32 gigawatts and the 7 years that are missing till 2030, that means that we have to invest to double our investment. We have to go to 4,500 gigawatt investment per year, so double that figure. For solar photovoltaics, we invested a lot in 2022. The investment ratio was 4,600 megawatts, and now we have to reach something like 7,500 megawatts per year. So again, the investment ratio is huge, and also for storage is really outstanding. So the message here is that we need to go faster. We need to speed up in our investment so that we can comply with these targets. When we have a look to the energy balance, then we see that also electrification will play a bigger role. So we will move, I mean, this is the data we have, the official data, so I took it. It has not moved so much from 2021 till now, and you see there that electricity was 24% of the final energy consumption. It is expected to reach 32%. So for sure, we see a move towards electrification. But when we see the numbers in absolute terms, we see that the increase is not so big. It's from 20 kiloTEPs, 22 kiloTEPs. Okay, if you now connect the previous data and this data, you see that there is like a mismatch. Yeah, we are doing a lot on renewable generation, but electrification is not increasing so much. That's also put some challenges in the energy system, because we all know that renewable energy, wind and solar, it's intermittent, and it does not match always the consumption. So, you know, we need to do certain things, otherwise we will have plenty of curtailments that it would be something that would not be optimal from an economical point of view. That's why the message we wanted to tell you is that we need to speed up also in electrification. There is much more that needs to be done on flexible demand, so that we can take the best benefit or the best advantage. We can take advantage of that renewable capacity that could be developed, hopefully in Spain. When we look to the renewable power generation cost, okay, we can have different data, but we know that the reduction in cost has been amazing, and today it is competitive. So today, here we have two things. We have the technology development. It makes economic sense, and we also have what we say in regulation, like the economic tool to develop that. There are, in Spain, I know in other jurisdictions it's also the case, there is a lot of development that is done through what we call a power purchase agreement. So this is no more than a long-term contract between a producer and a buyer, which can be a retailer or which can be a consumer, and they fix this long-term contract. So the price is set. This provides price visibility for the investors. They know the revenue stream, and for the consumer, they have visibility on their costs. So it is like a perfect match. We have production on the one side, we have consumption on the other hand, and then they match and they develop. So they both have a benefit. So this is something that is really moving a lot the renewable market today in Spain. We also need storage. So everybody that talks about energy transition, at least today in Spain, we all recognize the value of storage because we need to accommodate that intermittent generation. Here, we know how to do it when it is the case of pumped storage hydroelectric. It's cost efficient, the technology is well known, and according to the data of Iberdrola, we estimate that there are around 10 gigawatts of additional storage, pumped storage that can be developed that are based on one reservoir, so that you only need to maybe build the upper reservoir, not two, okay? So that means that there are 10 gigawatts that can be developed in Spain and could make a difference. But of course, it takes time and it needs an economic signal. When we look to batteries, we know the market is moving fast. We know it's decreasing cost, but we are not still there. We believe that the technology needs to make some more progress so that it is cost competitive. So here we have a technology that is mature, one that is promising, but when we look to the economic tool, we find that there is something missing. Because if you notice, there has not been much, everybody tells storage is needed, and there is not much storage development. So that's why, because there is no economic signal. Iberdrola has done has invested in some batteries. One is the one in the picture, it's in Spain, but it's more like pilot projects to also learn about the technology, not so much that it makes economic sense to develop them. What it's missing, what we call capacity markets. For you that are not familiar with this term, it is no more than a market that rewards capacity that is there when renewables are not there. So firm capacities that are reliable and that can be sure that whatever happens, the consumer will have their supply. So those are all the traditional technologies, I would say, and of course, storage. So this is something that's where the regulation mix also with technologies. When you see that something makes sense from a system perspective, but you do not have the economic signal, it does not move. So there is some progress in Spain in this regard, and we hope that we have this capacity market that it's already established at least in 8 member states within the European Union. So it is something that is quite common across the European Union. Okay, so here the message is we have renewables, they are cost competitive, they are being developed right now. We need the storage, we need the economic signal, we are getting there, but we need to match with demand. So once we have this power energy mix, which is decarbonized and which is also cost competitive because renewables are cost competitive, it makes sense to move towards more electrification in demand. This picture shows that the border of what makes, okay, so we say, what can we electrify? We can move into more electrification into transport, into industry, into buildings, but what does it make sense? Well, this border has moved a long time. So if you remember some years ago, people would tell you that, you know, we cannot go for an electrified bus. Today, everybody is considering that in the future, the buses, the urban transport will be 100% electric. So we have seen here also a technology movement in which we see that the electrification border has moved. And then we don't know where is the limit yet, but we see that every year it makes more sense to electrify. So that's why we say, you know, we have to try to electrify, and I can maybe use some of the slides of Professor Cabellos. You remember that we have to accelerate. You remember that curve that was steep. So if we, and the carbon budget concept, if we do not do what makes economic sense today, and we postpone that decision, it means our carbon budget, you know, we are using it now. So we will have to go steeper. So that's what we say. Let's go and let's move towards what it makes economic sense today. Do not postpone the decision in electrification in what already today makes economic sense. We will discuss about tomorrow whenever technology moves, if it moves, or if it's other alternative that is more convenient than electrification. So when we have a look to household, to the transport sector, and to the industry, well, I'll give you some figures for the Spanish case. That is the one that I know. On homes, it really makes sense, and it is expected, or at least the Spanish draft National Energy Plan expects that we more than double, it's more or less double and a half the consumption of heat pumps. So this has really a long go there. I would not say that we have to use a heat pump for everything, because, or at least what my colleagues tell me, they tell me that it makes sense for many things. It makes sense for individual homes. It makes sense for, you know, these buildings, blocks that have a common heater, and where you can take action in that common heater. But today it does not make so much sense when you have an individual boiler, because it's not so easy to put a heat pump there that makes, you know, that provides the energy you need. So we can discuss, you know, does it make sense in buildings? Yes. In every single apartment, maybe not today. We will see tomorrow. But it does make sense in many buildings already, and we can move there. The same for transport. These draft plans considers 5.5 million vehicles, electric vehicles in 2030, which is really something challenging. And we are seeing also progress in industry for low to medium temperature processes. So this is something which is almost there, and maybe we have to look more at what the industry needs, because they are, you know, also in the process of transforming and taking decisions now, and how they can go for this low temperature, which makes sense in many cases to electrify these processes. Of course, there are others that direct electrification will never be a solution, which is like high temperature processes, and for that, you know, we have green hydrogen that can also be can also be a solution in the future. We are in the process of some pilot projects there, and see how it moves. So just to finalize, I would tell you that there is something, you know, between the production and between the consumption. Of course, they are the networks that many times we have not paid enough attention to them, and today they are becoming, you know, a key for the energy transition. Why? Because the challenge is so big that they need to accommodate new, more distributed renewable. They have to accommodate more demand, which is completely different from the previous times. More electric vehicles, more heat pumps, you know, these industrial hubs where they will go to electrify, and we will be demanding eventually important increase of demand at a local point, and there will be congestions. So we need to anticipate. Grids need to do much progress beforehand, and anticipate these investments where it could be needed. So this also, again, the regulatory component comes here. The grid operator needs the framework to recognize that they have to go for anticipatory investments. That is something that was not needed in the past, and is needed today, and would be even more needed in the future. So we need also here a regulatory change to give the economic signal to these grid operators, so they move into what we are requesting, which is to move into the energy transition. And just to finalize, just to show you some scenarios, this was a report prepared by EurAsc, which is an European association of many European utilities. And you see there, it's a bit maybe, outdated, but it doesn't really matter. What I would like to share with you is that, in all scenarios, you see that electrification will play a very important role in the energy mix. Eventually, we will see where is the limit, but it is clear that it will provide a solution to the energy transition. Thank you very much.
Okay, so since this is a roundtable, we will leave the questions at the end of the table.
Thank you, Marisol. Thank you to Ms. Sara for your presentation. Our next speaker is Dr. Teófilo Rojo. You can see his CV in the booklets, but just to anticipate it, he has spent various research periods at the Institute of Condensed Matter in Bordeaux, in France, the King's College in London, the University of Cambridge, also in the United Kingdom, and the University of Campinas in Brazil. Since 1992, he has been full professor of inorganic chemistry at the University of the Basque Country. He has co-authored many papers, 550 articles and so on, and he has co-edited as well several works. He's co-author of 8 patents related to magnetic and energy materials. Of special note is the PCT patents obtained about the first nanohybrid polymer electrolytes for lithium and sodium from batteries. Please go ahead, and thank you very much. Please.
Okay, thank you for the presentation. First of all, I would like to thank Professor Miguel Alario for inviting me to participate in this interesting symposium. My talk today is, the title of my talk today is Present Challenges, Future Trends and Effect on the Energy Transition of the Battery Technologies. The presentation, I'm going to focus my presentation for the application of batteries, basically mobility and grid energy storage. So, after a short introduction, I'm going to speak about batteries for mobility, battery for grid energy storage, and to finish with conclusions and future trends. Well, the energy is one of the most important problems for the next 50 years. If we analyze, for example, here, in 2003, there is 6.3 billion people, and in 2050, 10 billion people, we can notice the importance that to increase the energy in the future. If we analyze where the energy is coming now, we can see that only 10%, but less than 10% is coming from renewable energy. And it's worth mentioning that this is an important investment in global clean energy in the last 2 years after the COVID pandemic and the response to the global energy crisis. In the middle term, the structure of the energy production and energy consumption will be related to the electricity with high efficiency and reliability, and with the hydrogen, green hydrogen, in order to have zero or near zero emissions. Energy storage is important for the generation, transmission, and distribution systems. Storage is critical. We have different aspects, for example, frequency regulation and load following, cold start services, contingency reserve, and also energy services that shift generation from peak to off-peak periods. Batteries constitute the critical part of the available energy storage systems. If we analyze, for example, in mid-terms, automobiles, if we consider only 10% of electrical cars for 10 to 9 cars, we need 210 to 6 ton batteries. For the load leveling, the production, if we store only 10% per day of the whole electricity production of 2030, we need 10 to 9 tons of batteries. We can observe the evolution, the annual battery demand in the years, and in 2038 is approximately 2,300 gigawatts hour. But basically, per year, basically from mobility and then stationary, for mobility and also consumer electronics and machinery. Battery technologies, if we analyze the evolution of the energy density with a gravimetric and volumetric in comparison with different battery technologies, we can notice that the best technology is the lithium ion and lithium metal. So, batteries for mobility. Lithium ion technology application. We have, for example, lithium ion batteries satisfy the portable and consumer electronic markets, watts hour. What about the electrical vehicle market? And what about the energy storage market? My question is the use of lithium-ion batteries necessary or appropriate in energy storage application, in stationary energy? If we analyze the evolution of the different generation lithium-ion batteries, we can see here the first generation and the second generation. They are commercialized. In the first generation, we have a cathode, we have a layer of site, nickel, manganese, cobalt, lithium iron phosphate. In the case of anode, modified graphite and lithium titanate. In the electrolyte, conventional organic electrolytes. Regarding the second generation, we have seen also that the cathode, the main material is the layer of size, nickel, manganese, cobalt, with different proportion. So, the question is, we have in these materials cobalt and nickel. We know that it's toxic and expensive material. So, we need to continue with this kind of materials. It's depends on. We are going to continue. We are going to discuss that in my presentation. In the fourth generation, is the solid-state batteries. We have probably for 2025. In this case, the main change is to use solid electrolyte, and in the Vision lithium, in order to improve the energy density, we have to move to metal air, metal oxygen battery, metal sulfur batteries, and using lithium as metal lithium. Regarding the metal oxygen and metal sulfur, at the moment they have in low TRL. It's difficult in this case, in these technologies, to have a good technology in metal air, lithium air, for example, in 30 years' time. On the contrary, the research is focused basically in all solid-state batteries. Why all solid-state batteries? The main advantages avoid diminishes the safety problems, high thermal stability, wide electrochemical stability window, stellar mechanical properties, and no dendrite formation if we use metallic lithium. The main drawback is the low ionic conductivity at room temperature. If you can use lithium metallic as anode, we can improve the volumetric energy density about 70% and the gravimetric energy density 40% respect to the conventional organic electrolyte. There are different solid electrolytes. Well, solid-state batteries, we use solid electrolytes, polymer, amorphous polymer, inorganic solid electrolytes, oxides, sulfides, halides, all of them in crystalline, in the polymer. All of them have advantages, disadvantages. In the case of polymer, the ionic conductivity is very poor. On the contrary, in the sulfide satellites, it's excellent. But in the polymer outside, the air stability is really good, but not in the case of sulfide and halides. There are different companies working in all these materials, except in the halides. That is, there is not company working at this moment in this. And the easy manufacturing is also depend on the inorganic solid electrolyte. Another important point is the evolution of the lithium. The comparison of the lithium global production, cost and demand. The lithium global production and the cost increases every year, except in the last 2 years, depend on the pandemic and the economic energetic crisis, but in the future it will increase significantly, all of them, lithium global production, lithium-ion battery cells in gigawatts-hour, and also lithium carbonate cost. What is the main barrier to expand electrification? The cost is the main barrier. Cost usually is commonly is considered $150 per kilowatt-hour is the point of commercialization of battery for electric vehicle. The ultimate goal should be $8 per kilowatt-hour, and also important, decrease the charge time to 10 minutes or less. Energy density. We can see this is the energy density. If we increase the energy density, obviously with an effect, a reduction in the cost. So, considering that the conventional lithium energy density range at the moment from 160 watt-hour per kilogram for using lithium iron phosphate to 275 watt-hour per kilogram, if we use, for example, NMC oxide, is nickel, manganese, cobalt, we can improve the energy density, but we need to move also to increase the energy density to 400 and 500 watt-hour per kilogram in order to reduce the cost significantly. Other important point is the toxicity of materials. As I said before, the companies are currently positioning in using lithium iron phosphate versus nickel, manganese, cobalt oxide, despite its cost in energy density. So, it's important the companies are thinking on moving in materials with low toxicity and cost, if possible. Lithium-ion batteries. Lithium-ion batteries is the best battery from the energy density point of view. We can see here that the theoretical energy density is approximately 12,000 watt-hour per kilogram on lithium only. It's quite similar with a discharge voltage 2.7. It's quite similar to the gasoline in theoretical and experimental. What is the problem? The problem is these systems are poor efficiency, poor rate capability, or low cycle life. As I said before, we need at least 30 years to move to this technology that is the best competitive technology from the energy density point of view. Batteries for grid energy storage. In this case, we are moving to a redox flow battery, so sodium sulfur battery. We have here one table with technology comparison of different batteries. The first one, the first one has have lead, nickel, cadmium, vanadium, and this is we know that these materials are not interesting to be commercialized. The sodium sulfur and Zebra, that very good energy density, very good efficiency, a good cycle life. The problem in this material, in these batteries, are working at 300 and 350 degrees C, a high temperature. If we move, for example, the other one, this one, is graphite and lithium oxide, cobalt lithium oxide. These are good energy density, but poor cycle life and good efficiency. And the last one is lithium titanate and lithium iron phosphate. We are using lithium in the anode, we are using lithium in the cathode, and the energy density that we have here is 50 or 70 watt-hour per kilogram. The question is necessary for a stationary energy application to use lithium-ion batteries? Other batteries in the market at the moment are all vanadium redox flow batteries. They have the key aspects are power and energy, are separate enabling greater flexibility and safety, wide range of chemistry, but the problem of these batteries are expensive, too high for commercialization. They are using vanadium is with high cost and toxicity. So the research is moving now on other materials, water-soluble organic materials, to replace vanadium in order to avoid the toxicity and cost of vanadium and to decrease the cost. If we analyze in the periodic table the different kind of batteries, we can notice that different battery concepts. In the alkaline, lithium, sodium, and potassium. In the alkaline earth, magnesium, calcium. In the transition, zinc, and in the post-transition, aluminium. People are working in all these kind of systems. Because large energy storage is a great challenge. At the moment, the best alternative for stationary applications, sodium-based systems, seem to be the best. Why sodium-based batteries? We have commercialized two of them, sodium sulfur and Zebra, but they are working at high temperature. So we had to decrease the temperature to move to low temperature of sodium sulfur to decrease the cost in order to have high energy. Another one is to work in sodium ion in order to decrease the cost and to increase the power. If we compare the properties of the lithium-ion batteries with sodium-ion batteries, we can see energy density. In the case of lithium-ion, we have 150 watt-hours per kilogram with lithium-iron phosphate and 275 watt-hours per kilogram for layer oxide nickel, manganese, cobalt. In the case of sodium, we have at the moment 160 watt-hours per kilogram and to move up to 200 watt-hours per kilogram. In the cycle life, there are good cycle life in the case of lithium, 6,000 cycles for lithium iron phosphate batteries. In the case of the sodium, we can arrive up to 50 kilocycles if we use aqueous electrolyte. Good low temperature performance, fast charging. Raw material cost is very, very competitive in the case of sodium versus lithium, and safety, there is no risk of thermal runaway in the case of aqueous electrolyte. And also, in the case of sodium, they don't need, sodium batteries, they don't need recycling. Companies currently are working and investigating in all solid-state batteries and in sodium-ion batteries this year. We can see here all solid-state batteries with the companies, with the partners, in the United States, Canada, Japan, Korea, and Europe. In Europe, we have only one already, with different electrical car companies. And in the case of sodium-ion batteries, they are working in China and the United States. CAT is the best company at the moment, but there are other companies like Hina. They have an electrical vehicle with a low speed, 70 kilometers per hour, but with sodium-ion batteries, not toxic and not expensive. And BID, we have working also in sodium-ion batteries. In the United States, we have Natron Energy working in aqueous electrolyte with very, very competitive batteries. For conclusion and future trends. Conclusion, electrochemical energy storage depends on the applications. For energy storage for vehicles, electromobility is a reality with current lithium-ion batteries. Beyond lithium-ion batteries are required to satisfy the market needs, to improve the energy density. Metal air is still far from reality. Lithium sulfur is a future technology, but from my point of view is all solid-state battery with lithium sulfur. It means using solid electrolyte. Energy storage for grid. Cost is a determinant factor in stationary energy storage. For vehicles, energy density, but not for grid. redox flow batteries should be improved. Aqueous organic soluble salts could be the solution. Sodium sulfur and Zebra batteries are successfully commercialized, but they need decrease the operating temperature. Sodium-ion battery technology can contribute to stationary energy storage because the energy density are quite similar to conventional lithium-ion, and existing lithium-ion manufacturing lines can be used to make sodium-ion batteries. And very important, developing advanced materials is the key to clean energy and clean mobility technologies in the future. Will soon account for 80% of the technology manufacturing cost. The vision and mission for Battery 2030, Europe needs to lead the discovery and manufacturing of ultra-high performance batteries. Also, to create a competitive industry for long-term prosperity and security, and to accelerate the discovery of ultra-high performance materials and interfaces for the batteries of the future. To be competitive in Europe for the next 10 years, we need to think in smart batteries with intelligent functionality. Smart batteries and sensing, and battery self-healing. Other important aspects are manufacturability, recyclability, and sustainability. If we analyze the global electric vehicles forecast, we can see a significant increase in the next 80 years, with approximately more than 20 million sales global by 2030. So we need a lot of batteries. We need gigafactory. The question we have here, we have here a roadmap for gigafactories in Europe and in the United States. I have a lot of questions about that. First of all, how many projected gigafactories will remain in the future? Also in Spain we have five projected. Excellent financing through the Next Generation in Europe funds. But the problem here is not transparency in financing consortium. And also, how have the evaluation of the presented projects been carried out? This is an expert commission. Who is the responsible to give this the funding for this technology? Another important point is the top 10 electrical vehicle markets are involved in the raw material supply chains. There has been a notable pickup in strategy investment into the raw material sector since 2025. It means the red cycle is in the after 2025. It means this is a very important thinking in the case of the involvement of raw materials in the companies. As I said before, some companies are moving to lithium iron phosphate instead of layer oxide cobalt nickel. Why? Because less energy density, but very competitive from the point of view of toxicity and so on. And the last one, And finally, with this, this is the evolution of the electricity that we need, and only to mention that we need recycling. We need to improve the recycling in basically in lithium-ion batteries for cobalt, nickel, lithium, and copper. That is not the case of sodium-ion batteries. And thank you very much for your attention.
Yeah, questions at the end. Thank you so much, Professor Rojo.
Yeah, okay.
So we are going from electrified future to batteries, and now we have windmills. The talk is going to be given by Amaya Igartua, which is the actual coordinator of the European actions in materials in the research institution Techniker, and is co-secretary of the European Platform of Materials EUMAT and the Alliance for Materials. She has been running over the last 10 years the head of the unit of tribology in Techniker, And she's going to give us a talk about increasing the energy efficiency of renewable in windmills use. The floor is yours.
Thank you very much for nice presentation and also for the invitation to this event that is fantastic. It's an honor for me to be here today, and thanks Professor Rodrigo Martins for the invitation. The presentation of the talk is increasing energy efficiency and renewability in windmills. And I will try to explain why, because windmills are renewable energy, but still they use mineral oils or synthetic oils, and the idea is that it is used also in the future renewable lubricants for windmills, and this is the point and share the experience that we have in this sense. And the presentation that is here is bringing together with Techniker, Bureau Veritas, and Atentu. There are two units that has been one unit, the lubrication management, has been sold to Bureau Veritas, and Atentu is a spin-off company that has been created initially by Techniker, but also now with the support of Verdola, and it is now a company, independent company. And I will present also this initiative. Then first I will present Techniker, one slide. Another tribology, the tool for design safe and sustainable by design products, because I am tribologist. I've been working more than 30 years in the field of tribology, and the experience of the bio-based renewable high oleic sunflower oil for lubrication in windmills and other type of application, also nanotechnology potential for lubrication, and the need of condition monitoring to extend the lifetime of lubricants, because especially it's important to the cost of the maintenance is important in order to assure that the price of energy is at low level. Smart sensors to reduce the cost of maintenance, specifically is possible to control online the windmills, then we reduce cost. The conclusion and also the lunar conference that we are organizing for 2024 that I will share with you. Then first, Techniker is a research center located in the north of Spain, in Eibar, between Bilbao, San Sebastián, and Vitoria in the center, and is a research center that is already 42 years old. And we develop technologies to transfer to the industries, and we are dealing with manufacturing, with materials, and also technologies in order to help industries to upgrade the skills. And we have 25.6 million euros turnover with 270 employees, but also we create some companies, 32, and from that we still keep the stakeholders and attend to HMTK, Hydrogen Green. Also we invested in a hydrogen company. Masermic is microelectronics, Tribomat, this is European Center for Tribology, and with that we achieve 48 million euros with 366 employees. Then why tribology? The tribology has an importance because 30% of the world energy consumption is lost in the way of friction. Then if we can influence in the materials and lubricants in terms of increasing lifetime, then we will going to save a lot of energy and also materials in order to deal with Green Deal objective. Then this will also help to reduce the carbon footprint. Why the tribology is a safe and sustainable by design tool in order to develop products? Because if we introduce in the design of the components and in the properties of the materials, their durability, that is not the case right now, then it will be possible to influence in a design for durability that will improve the guarantee of the products, but this will require to do at the laboratory study, simulate the working conditions of the real application, reproduce the mechanism of failure at the laboratory, and try to find which is the solution of the material that is possible in order to increase the lifetime. Then what is the lubrication challenge in wind sector? The right lubricant can increase the energy production while lowering the capital cost. This is turbines are located in remote locations, then if it's costly to repair the failure of a component, then we have to avoid the failure of any component, and the control of the lubricant is similar to the control of the blood in one person. That means that if we control the status of the lubricant, we have a lot of information about what is the status of all windmill components. And what are the requirements of the formulation? High scaffing resistance, micro-pitting resistance that avoid the fatigue damage, compatibility with paints, elastomers, and also protect from leakage of lubricant, excellent aging and oxidation resistance, sufficient lubricant film at high temperature, pumpability, and wide operating temperature rates. And why high sunflower oil is only one of the possibilities of renewable lubricants that can be used in windmills, but I highlight because we have had experience with this type of lubricants, and it's vegetable oils and has a content of high oleic sunflower oil, is cultivated in Spain, and have a quite good stability to the oxidation due to the increase of sunflower oil. And also the soft refining process that was done since sunflower oil is prepared for food, then it's possible to reduce for using for industrial application. It's possible to modify the production process in order to be more appropriate with lower cost. And how is the oxidation resistance of these lubricants? Then if we can carry out two types of tests. One is the dynamic method, that we see that the temperature resistance is similar or still better, but it is necessary to control the oxidation with time. And what are the properties of the biolubricants? That is biodegradable. That means that if it's an accident, they will be biodegradable, and it does not mean that it's possible to throw to the land, but if there is an accident, it could be biodegradable. And ecotoxicity, that means that it is not toxic. That does not mean that it's possible to eat, but the concentration is E50 is higher than 100 milligrams per liter. That means that it's not toxic. And also the control of additives, there is no contain at all any toxic additive. And how we measure at the laboratory scale the properties of the lubricant comparing with mineral oil, for example. Then if we measure the friction and temperature, it's possible to see that the friction coefficient is lower and also the temperature is lower. This causes less friction and less increase of temperature. And also it's possible that to see that the wear properties are good, are less wear damage in the biolubricants comparing with a mineral oil, and also the FZG test that is the test in gears show that it is possible to reach a failure low at the stage of 12. That means that have good properties from the point of view of sensor. And also to highlight that also it's possible to improve the additivation of the lubricant using nanotechnology, can be nanoparticles or graphene, or also by microencapsulation in order to control the temperature during time, but it is possible to see that only with very small quantity of nanoparticle is possible to reach a substantial reduction of the wear scar. But one thing that is important is to control oxidation, as we have highlighted. Then it is important to control the oxidation evolution, because we accelerated the lubricants at the laboratory scale, and we saw that there is an interrelationship between the oxidation increase and damage. Then it's possible controlling the tan number, that is the acid number, is possible to control also the welding in the system. Then analyzing with that, also with some parameters that is possible to control in the lubricant, we saw that it is important to control that the acid number is not higher than 1 milligram the QOH, because if this is higher than this quantity, then it could start welding in the component and damage the bearing and other part of the component. Then it is also necessary to carry out a failure analysis. That means that if there is any failure, it is possible to analyze what is the reason of the failure, and to try to avoid this failure. This is all this failure mechanism possible to analyze in the laboratory, and to give a solution in terms of material. And then lubrication management, as we saw before, is a lab accredited with ISO 7025, and was adquired in January 2018 from Bureau Veritas to Techniker, and now it has been integrated to Bureau Veritas, but it continues in Techniker, and we have a strong collaboration. They are doing the oil condition monitoring, analyzing the lubricants of day by day with different samples, and controlling the lubricants of different installations, including windmills. And then there is an operating protocol related to the sample, reception, oil analysis, results analysis, and reporting. It is very important role in the energy sector, because they can control the turbine, generator, transformer of gearbox. They are working with different companies. Then it's possible to have, let's say, a direct information about the different system in different position, and it is analyzed depending of the system, the sampling period that can be 6 months of 1 year. And then each company can control their sample, and it is possible to have a customer information, equipment information, oil condition monitoring, the information of the oil contamination, the wear debris, and the diagnostic. And then it is possible to control if the machine is okay or not. Then, as it was mentioned before, the limits of each parameter that is controlled during the assessment is analyzed and compared to a reference of the same system and a reference of all the systems, and with that visual analysis is established, and then this visual mapping can be made with several aerogenerators that can be controlled at the same time. And then I will show also the company Attentu that has been the spin-off from Techniker, second spin-off. And this company developed sensors in order to control online the status of the lubricants. And with these companies, these are the oil sensors that measure the wear particles and also the status of the oxidation of the lubricant. And it is located, the sensor, in the aerogenerator, and it is also controlling the wear particles, and it is created advanced algorithm based of analysis of the wear particles and also the status of the oxidation of the lubricants. The oxidation is controlled by colorimetry, and the particles is controlled by counting the sediments and pollutants and analyzing the filtering the efficiency. This is the fluid sensor solution, and this is the two sensor, and also how is possible to control on the remotely, and how this is related with the standard assessment in order to revise the evolution of the wear particles and to relate with any type of failure, because with the size and shape of the wear particles, this gives information about the failure mechanism, and the degradation of the lubricant is shown with the aging. And then to show that it's possible to make savings also, and it's possible to reduce the cost of maintenance until 30%, and also this reduce the risk of maintenance of the aerogeneration, also avoid failure as cost level, and combining sensor tribology and condition monitoring is possible to assure that the aerogenerator can work perfectly without minimizing the risk. And this is the conclusion, that it's possible to use biodegradable lubricants, but it's necessary to control the oxidation resistance. It's possible to use nanomaterials to improve durability and energy efficiency. It's necessary to determine the oil change frequency and make a methodological analysis if there is any problem, in order to find the reason of failure, reproduce the failure at the laboratory, and find solution in order to avoid this happening in the future. And the performance of the lubricants during use, it is possible to control by visual inspection, but also by oil analysis using sensor. And this is the LUDMAT conference that we are organizing the 18-20 June 2024 in San Sebastián. If any of you are interested, will be welcome to the north of Spain.
Thank you very much, Professor Amaya, for your excellent presentation as well. Well, our last speaker today is Professor Juan Ramón Morante. He is group leader of Energy Storage, Harvesting and Catalyst Group. His activity focuses on the introduction of renewable energies and the environmental impact of energy. Likewise, he's involved in the deployment of new energy carriers such as hydrogen, biomethane and synthetic fuels for a sustainable mobility, a decarbonized industry, cities and society. Professor Morante is going to talk about defossilization, electrification and circular economy. Please, Professor, the floor is yours.
Thank you for inviting me to be here. Thank you for this introduction. And I am going to talk about some objectives. So, roadmap. What is Europe is moving? As you can see, is to avoid CO2 emissions. But to remove these CO2 emissions, we need to defossilization of many activities. One is the energy production, the other one is the chemical industry, refineries, for example, but something that this today I don't listen many comments, transportation. The main consumption of energy is oil. In many European countries is almost 50%, 47% is oil. And this oil is mainly used for transportation. One part to the industry, but the main part is transportation. So, if we want to avoid the emissions of CO2, of course, we can proceed in the electrification, residential, service sector, industry, but transportation is something that is there. Okay? And then this is the roadmap, just to arrive in 2050 to net zero carbon emissions. What we plan to do is first efficiency. If you move something to electrified process, sure that you are increasing the efficiency, because many combustions process is less than 28%, thermodynamic rules of efficiency. If you are moving to electrification and you are using an electrical engine, sure that you are more than 90%. So this is the objective. But if the electrons in the plug are not yet green, what is the mean of the electrification? So we need to start with introduction of renewables energy, and then something that we need to do is also to be sure of the circularity, especially concerning the feedstocks, the waste. So this is the new concept of circular economy. So this is more or less the objectives that Europe are putting on the table. So, second point. So, no fossils, then it's mandatory the energy transition. We need to develop new models of energy and to be in mind that we are in front of a new geopolitical map. No more the geopolitics of the oil, no more the geopolitics of the gas. This is the production of wind energy, this is the production of the solar energy, and okay, we must consider pumping, hydraulic power, also geothermal power, bioenergy. Okay, this is defining, and you can understand why Germany is signing agreements with Namibia, because they can produce wind energy and they can produce, for example, solar energy. And also why Rotterdam Harbor is signing agreements with Uruguay or with Argentina, because they can produce a lot of wind energy, for example. And of course, then another problem is how to transport this energy. And this is something that I put to show something. Renewables are tied to the use of energy storage systems. And we have the electrochemical solution, batteries, but density of a battery is 250 watt-hour by kilo, but the gasoline is 11,000. So this is a serious problem. Today, the energy carrier is the gasoline, and we need to replace this energy carrier. This is the reason that exists hydrogen, biomethane. So the objective or the requirement is how to storage energy in a chemical molecule. Hydrogen, biomethane, or just synthetic fuels, or just some other chemical compound. So this is in the roadmap, we need to put these new carriers, energy carrier. This means first the green hydrogen. The second is what we can do with the CO2. What is the difference in decarbonization or desfossilization? Decarbonization means that you are removing all the carbon, but this is not realistic because there are many products that you need carbon. And then this is the problem. From where I am going to obtain this carbon? So this is the 5th point in my presentation. We are using a lot of organic or just plastics, polymers, some fuels that are based on hydrocarbon molecules. So we need to replace the carbon for non-fossil carbon. And we need to develop a new chemistry, new sustainable chemistry of the carbon. But 3 key points. Efficiency, because in the laboratory it's possible to demonstrate many things. But for the industrial sector, you need to demonstrate efficiency of the process, productivity. Just to produce 10 molecules by second is not enough for the industry, so productivity. And the other point, critical point, is the feasibility, industrial feasibility. What is the lifetime? What is the, if you are doing an investment, what is the rentability? What is the duration of this investment? So CapEx and OpEx, finally. So this is defining the reliable and competitive cost of this alternative. From the science, you can elaborate many of these plots. From water, from CO2, you can produce hydrogen, you can produce carbon monoxide, syngas, Fischer-Tropsch, and you can produce synthetic fuels. You can use the fermentation process. You can produce C2, C3 products. Sabatier reaction, you can produce synthetic methane. From C2, 3 molecules, you can produce ethylenes, so plastics, polymers, synthetic methane, and also the nitrogen. This morning was showed the question of nitrogen. Even better to use nitrates because it's much more easy from chemistry point of view to reduce, starting in nitrates, just to get ammonia. What is our knowledge, scientific knowledge, are offering to do this process? The sun is the original energy. You can produce heat or you can produce electricity. And then you can capture the CO2. Critical point. We are going to discuss about the capture of CO2. You can capture the CO2 from biogenic source, waste, organics, farms, biological systems, or from the air, or from the sea, ocean. This is let's go to discuss these 3 possible origins of the carbons. And then you have feedstock, CO2 and water, and the scientific knowledge, and the technology associated to this scientific knowledge. Photolysis, photocatalysis, photoelectrochemical, electrochemical, thermochemical, and thermolysis. Production, efficiency, and feasibility are better values in two of this process, that is thermochemical, and we can associate electrochemical and photoelectrochemical. The other possibilities are getting lower values of productivity and efficiencies. So we are going to be concentrated in these options. So, to develop these concepts, no fossils, we cannot use oil or gas. And then what options we have to get carbons? Green carbons is one option, biogenic origin, and the other is that in the literature is known as neutral carbons. This means carbons that has been removed from the ambient. No carbons that are coming from fossils, because if not, we never close the circle. No fossils, from where I can obtain carbons. Green, or just from the air, or from the ocean. DAC and DOC. This is the official name for this carbon capture process. With these carbons and hydrogen, we can apply thermochemical transformation or electrochemical transformation. The other processes are artificial photosynthesis and natural photosynthesis, but we are interested in this thermochemical and electrochemical as alternative for the future. Many challenges: productivity, electrochemical process. If we are not able to arrive to even near amperes by square centimeter in the electrodes, productivity is not so interesting from industrial point of view. So this is one first challenge. And the second is the Faraday efficiency. I can introduce the energy to the molecule just by electrons, but all the electrons are reacting. So this is the Faraday efficiency concept. Still are very good values in some products, formic, carbon monoxide, methanol, but still ethylene, that is quite interesting for the chemical industry, or for the ethanol, efficiencies are still very low. And then hydrogen, the three possible origins from the carbon, and this is the basis for the fossilization. But to be successful, we need to improve this process. And for this, we need to improve this is the challenge for the scientific people, is rational design of the catalyst material. This is the main problem for the scientific people, how to improve the rational design of the catalytic, just to increase productivity, efficiency, and also to get very long lifetime. Observe, capture the price of the ton of the CO2. Today, the technology are using almost more than 3 electron volts for molecule. This means that for 1 ton you need 2 megawatt hour of energy. What is the price of the energy? Megawatt hour of energy. So this is the reason that, for example, direct capture from there is 300, 400 euros by ton. This is quite expensive. And then you need to, this is this red line, you need the energy that you need for the process. So this is the final cost. If this line is here, this means that it's more expensive than the present technology. This is the black point. You need to reduce the cost of the carbon dioxide capture, just to get this line starting here, and then the slope that depends of the price of the energy. Here is electricity, consider it 50 euros, but you can simulate that you want, and you can estimate if these alternatives are or not competitive or can be competitive. But if the price of the capture of the CO2 is 300, 400 euros, forget. This is not competitive. Today, there are systems that the price is in the range of 80 euros by ton, and scientific people have always the idea of the threshold. What is the minimum energy that I need? It's about 0.2, and this is more or less this position here. This costs 20 euros. So this is the big challenge for the people, for the fossilization of our society that need to capture CO2, is to reduce the cost of the capture of CO2. Okay, and then to improve the other parameters, you need to apply science, rational design of catalyst. No time, but you can imagine it. You can put here all your creativity, all imagination, and you can define different nanostructures, different support, material support, different shapes, polyforms, intercalation, core shells, alloys, bimetallic combination, and even single atom catalyst ideas. That is a very nice idea, just to improve the capacity. And just to finish, 2 examples how you can contribute to improve this technology. Observe CO2 to carbon monoxide. Okay, you have 2 steps. You have 2 steps. And then in the first step, maybe you need 1 catalyst. And for the second step, it's better another catalyst. And then the challenge is possible to combine 2 catalysts. For example, in this case, we try to combine, after analysis of the characteristics of the first step and the second step, I try to combine nickel and iron. And we arrive to the idea that for the first step, that is the proton couple electron transition, is better iron, because have better parameters, and in the second step is better nickel. So the idea is it's possible to make synthesis getting 1 atom of iron, another of nickel together, just to stimulate this transition. Okay, this morning the colleague Hermenegildo was talking about the MOF. This is based on MOF design. And the other is thermochemical example. For example, this is a mesoporous seria, and this is a nanoparticle of nickel. What do you need to transform CO2 in methane? This is just I can capture CO2, and then I can make synthesis of methane. I need hydrogen. And then, observe, I need 2 materials. Material 1, just to dissociate the hydrogen. For example, nickel, nanoparticles of nickel. And the material 2 is, I need 1 site where the carbon dioxide can be blocked. And then I can make a shower of hydrogen, spillover of hydrogen. So, how to combine these 2 materials? How to get seria +3, because I have seria +4, the absorption of CO2 is not good. So, this is one example of the design. I put nickel. The nickel is producing a spillover of the hydrogen, and this hydrogen is reducing the seria +4 to seria +3. Immediately, CO2 is absorbed, and then is fixed there is fixed there and can receive more and more hydrogen until be transformed from CO2 to methane. This is that we was, and it's possible to determine that the concentration of the seria +3 is decreasing as you are going away from the nickel particle position. So that demonstrate the effect of this. Well, this is a detail. Just to finish, the time is running very fast. Just to finish, yes, I finish. The last slides. Ideas. I was talking about the rational design of catalysts, but don't forget that this is in the laboratory, but then you need to introduce this catalyst in the real reactors. And the real reactors are using these spheres, big size. So this is another step, how to move from the catalyst to technological catalyst. That is different. And the second is we need to improve the reactors. This is a different example of reactors. One based on plasma, another is not. And also, for example, this is a practical pilot plant that we was doing in Sabadell, just to produce methane from biogas. To finish, last one. Too many challenges. But as to summarize, the roadmap, the new geopolitical of the renewable energy, the requirement to get new carriers, energy carriers, and then the difficulty in the capture of CO2 just to get one alternative in using carbon products, but not fossils. And the dream, the final dream of the European roadmap is to get molecules directly from the sun. This is a prototype that we was doing with, this is in Móstoles, in Repsol. This is a prototype that was developed from EurASc, just to produce directly from the sun, in this case, hydrogen. Thank you for your attention.
We will start with the questions, comments.
I have a question for you, Sarah, my dear student. I have several questions, in fact. One is, you talk about electrification from 2030 to, from now to 2030. You said it's true that we are in the 20s and we go to the 30s. And my question is, which is the expectation for 2050 or 2060? This is my first question. My second is, you said in some moment that we arrived with an 80% of renewables. That's absolutely unrealistic. Absolutely unrealistic. After talking about the batteries in a storage, not batteries for 80% when? The question is when, which is the time schedule. And the third one is, what about hydrogen? What Iberdrola is thinking about hydrogen?
Okay. It's okay now? Okay, interesting question. Thank you for that. So you mean about electrification after 2030? I think I did not go into that detail, but I think I can maybe jump into other presentations. So when you see in a decarbonized economy, we only have renewables. So this is biomass, waste, wind, solar, and whatever hydro, whatever we have there, yeah? So electrification, I mentioned there is a limit, you know, of direct electrification. We still don't know where we will get there. Of course, we need to in our view, we need to electrify it as much as possible because it is the most efficient way. We use less renewable energy for that application when we go for direct electrification. Eventually, there will be a limit, and that limit, we expect that it still can move a little bit more, but then we have to go for something which is an energy carrier. It can be hydrogen, it can be a synthetic fuel. Of course, biogas can also have can play a role. We see it more local consumption of biogas, but of course, all that will have to be used because there is not so much resource. But you see that the technology is not so clear yet. It's more challenging. So that's why we will have to wait and see. We hope we get there, but still it's clear that we do not have the picture clear. So there will be a lot of what we call indirect electrification. One way is green hydrogen. It's a process that it is well known. It's also about the economy, and it's also about the cost of electricity and the advantages that can get there. So I hope I answered the first question. The second question you mentioned, it's unrealistic. How we see it in Iberdrola is that something else needs to be done. And that's what I try to share with you. And it is that we have to go faster in electrification, because otherwise it can be done. We can have a generation mix which is decarbonized because we know how to do it, but it will probably not be optimal. If you see a little bit the details of that Spanish energy plan, it's also considered that there will be a lot of exports, also hydrogen exports, that can be questioned. In any case, without entering into that discussion, we believe that something has to be done in demand. That's why I mentioned we have to go faster. And everything that makes economic sense today, we should go for that, so that we go, from a system perspective, closer to the optimum. And I hope also I answered to that. And then hydrogen, of course, we are there. I think we believe it's promising, but unfortunately, I think nobody sees that before 2030. So Iberdrola had one of the, I think in Europe is the biggest one, of 20 megawatt hydrogen plant, which is providing hydrogen to Fertiberia, which is a fertilizer Spanish company. And so we are proving the technology, and we are ready also to make some progress if we can, if we get also the financing from investment programs and research programs. So we are really consider that that's a possibility. We also have other projects, methanol projects, but this is much forward-looking. It's after 2030. So until 2030, I think we have to go with biogas, if we can use it on a local basis, very welcome. Direct electrification, very welcome. And then, of course, start looking forward to those developments that we should get them if we want to go for that, comply with those difficult targets.
You were a very good student. You followed me very
Congratulations.
My question is for Professor Rojo.
Yes?
You didn't, as far as energy storage, you didn't mention supercapacitors. Is there any future of those in this?
This is a good question. Well, sure, this is a good question because Professor Alario asked me to speak about batteries. But for me, supercapacitors, this is important because we are speaking energy for batteries and we are speaking power for supercapacitors. There are many groups now, companies working in hybrid. It's one Fardike batteries, another one supercapacitor. This China's Japan company, there are many companies. This technology is also important for transportation. In Spain, we have a company, CAF,
in the Basque Country. They have, for the tram, they have supercapacitors. For example, in Sevilla, in the center of Sevilla, you can have catenary. And they use supercapacitors. There are 4 supercapacitors, double layers, and 1 battery now with lithium-ion batteries. They use this one for transportation in the center of the city. But what is the advantage of the supercapacitors? This power. You need, for example, you need to stop in a bus station, for example, in 20 seconds you charge your supercapacitor. That is excellent. I like this material. The problem is they are very expensive. They are very expensive because the materials are expensive. But if we are thinking hybrid, for example, this is, I think, is a very, very good technology for the future. It's a good question.
I think this is on. I just have a general comment, I think, to everybody here, really, that if you become carbon neutral by 2050, this does not mean you're climate neutral. Because when you talk about the emissions of of carbon dioxide, what you need to do is include the emissions associated with nitrous oxide and methane, which are 20 gigatons per year. So the question is, and you should really make these statements in terms of the CO2 equivalence. So it's not just CO2, but it's the CO2 equivalence when the methane and the nitrous oxide effects, because the warming potential of those two gases is much higher than CO2, in fact, they're included in the estimate of emissions. So if you look at the last IPCC report, they're reporting emissions of 60 gigatons equivalent CO2 per year. And that has to come down to about 30, by 2030, this has got to come down to about 30 gigatons CO2 equivalent per year to arrive at 1.5 or 2 degrees. And this is, so we have to decarbonize, also including the other trace gases by about 7% per year from now until the end of this decade. So my question is, how do you deal with the 30% of emissions which are not associated with carbon dioxide?
Yes, in principle, the program, the decarbonization program is starting in mainly thinking in the companies, in the enterprise. This is the first objective. The reason is that in the next year will be the new system of the taxes to pay the emissions. And then when you are considering a refinery, a big complex of petrochemical complex, for example, we have in Spain, in Tarragona, one of the bigger ones in the south of Europe. They are emitting near 1 million of tons by year. And if you are estimating the cost of in principle, 90, 100 euros by ton, this is the current value of this tax. This means that these companies need to pay about 100 million of euros. And
my question was about the non-CO2 emissions. I mean, this is for I was actually asking about the non-CO2 emissions for nitrous oxide and methane. How are you dealing with that?
Sorry?
I mean, there are 3 greenhouse gases. There's carbon dioxide, or water vapor as well, carbon dioxide, nitrous oxide, and methane. What the discussion has been about almost the whole day is about carbon emissions. And what I'm saying is, if you go CO2 neutral, this does not mean you're climate neutral, because you have the other emissions of nitrous oxide and methane.
Well,
and so what can be done about that?
That is if you are using neutral carbon and you are applying the synthetic, for example, the synthetic fuels, of course you are going to emit the CO2 again, but you are removed the CO2 previously, but you are going to emit another gases that are producing also the effect. This is the reason that that I was explaining that the policy is to try to introduce in many processes that the industry need the heat first. If this temperature is not too high, the heat pumps, but this is limited. You cannot guarantee production of heat, very high temperature, and then they are, for example, the ceramic industry. They are.
I'm talking about the land use emissions. I'm talking about agricultural emissions.
Yeah. No. But But fair blocks is no. Sure. But I am talking about industry and then the residential and then the agriculture. In the industry, finally they try to replace by using hydrogen, because this way you can produce high temperature and you can avoid emissions of the CO2. But there is still a challenge, because the combustion of the hydrogen is high temperature, and the probability to produce NOx is increasing a lot. And then this is a remaining problem for the industry. In residentials, this will be electrified. In the field, at the moment, at least so far I know, there is not actions to try to reduce these emissions of the CO2. Maybe this is in all the basket of the emissions of the CO2. This is, I believe, it's 10%. So the more important is the emissions that is coming from industry and the emissions that are coming from transport. And then the actions today is just focused in these two blocks. And I believe that concerning the emissions, for example, from the agriculture, is in principle is the landfill emissions. This is, I don't know any strategic plan about these emissions.
Maybe I can formulate a little bit the discussion. Okay, I think that in the internal combustion engines, one technology that has been used is the technology that uses the recirculation of the exhaust gas. And that means that now it is recirculated, then it is possible to emit less gases. And another is the catalysts that are used in order to reduce the emissions. Then the emissions in the cars, in the combustion engine cars, has been reduced a lot. Additionally, in the cities, the batteries that are being electrical cars also will reduce the emission in the cities. That's, the battery is an energy vector, or the hydrogen is an energy vector. That means that you are not producing energy there. But if you consider the contamination at the level of the cities, then can be an advantage. But in any case, the movement towards reducing the emission also in combustion engines has been improved a lot, and also regulation at the level of the European Commission worldwide. That means that if we go also to synthetic fuels and if the fossil fuels disappear and we go to synthetic fuels, then it will be possible because we have the technology in order to reduce the emission still more than what we have. But it has been reduced tremendously. And additionally, from my point of view, the important is that when we are developing a process or a product, we calculate the life cycle assessment of this product and try to improve the life cycle and also quantify what is the environmental impact in terms of emission to water and environment, because it's not only CO2, what else should be considered. And also to calculate the monetization of the environmental impact. That means that because normally the companies are calculating the conventional cost, but if this environmental impact is monetized, that means converted into cost, this applied to the accounting of the company, it will be possible in the future to consider those aspects, not only environment but also social aspects, that if are quantified in terms of cost, then the companies will be more aware of the environmental social impact, and they will be more sustainable at the end of the life. And as I mentioned, durability, reusability, reparability is really important, and we try to use less resource during the life cycle of the components. Then we will save a lot of energy and materials.
I'm asking about other greenhouse gases.
Yeah.
I'm asking about methane and nitrous oxide emissions.
Yes.
How are you going to deal with those?
With catalyst or gas recirculation, as I mentioned at the beginning. I think that if you introduce in the engine again the exhaust gas, not total, all of that, but 30–40% of the exhaust gas you can reintroduce in the engine.
You are using hydrogen in combustion. If you are using hydrogen in the fuel cell, that's no problem. But if you are doing combustion of hydrogen, this can be a problem.
But methane comes from animals. Methane comes from livestock.
I think that we only can solve the problem of John if you kill everybody. That's the reality, because I think this is something that we have to take care of in the future, because when we say reduce to zero initially, we have to kill all the people. without the problem that John is raising. So we did not take care about it. Anyhow, I would like just to put the question to all of you. I think that the concept of solar...
Microphone is arriving.
Okay. The concept of solar refineries. What do you think that we will install in the future in the houses, the solar refineries, where we can storage energy, I can produce energy for my vehicle, I can have thermal energy coupled. How you think we are far from this concept? This is for you. And the other one is, we spoke about different topics of energy. But there are one, which is the piezoelectricity, the thermomechanical transformation of energy. So we can use all because I believe that we will not kill the cars, so we can use this to energize and the power. How far we are from this?
Well, I start. So the solar refinery has a problem. If you are converting the energy from the sun in electricity, you have today 22–24% of efficiency. If you try to do directly to move the energy of the photons to a chemical molecule, like photocatalysis or something like this, the efficiency is very low. And then today all the technology is using the energy from the sun, just applying photovoltaic, and then you are producing electricity, you transport electricity, and then you are developing electrochemical process, for example. Okay, and this is getting higher efficiency than other solutions. So directly is very nice, scientifically is fantastic, you can develop very nice idea, but the values are not acceptable for the industry because productivity is very low. Today there are one option, that is photoelectrochemistry, that you try to modify the photovoltaic device just to be at the same time the electrochemical electrode. Okay? Yeah, and then you can apply photoanodes or photocathodes. And some people has presented very nice efficiencies around maybe not 22, 24, but they are 15, 18%. And then this is one option for the future. This is about solar refinery. So it's a very nice, it's a fantastic idea, but there is the steps to take the photon, to move the energy to the molecule, and then to oxidize or to reduce, and then this finally. Yes. Yeah. No, yeah, but finally that is interesting is the productivity, and then if the efficiency is yes, yes, yes. And the other question that you put is thermomechanical. Well, today we talk about energy storage systems, batteries, and maybe chemical storage. I can explain you some arguments of one company that was analyzing to storage energy using hydrogen. And they say, I can produce hydrogen, efficiency 65%, and then I need to expand some percentage of this energy to compress or to make liquefy the hydrogen, or just to make pressure. I lose some energy. And finally, when I need to recover the energy in electricity way, the efficiency is again 65%. Then you multiply, and from the sun to the final electricity, maybe is 32% of efficiency. This is more than the gasoline in internal engine, the combustion engine, but it's low. And this company say me, maybe, and at this moment they are analyzing the possibility to make a compressed air system. Because the compressed air system, the efficiency, even in the worst of the case, that means that when you are compressing, you lose a lot of heat, okay? And then when you are recovering, you need to apply some heat. Even in this case, the efficiency is 45%, more than if you are using hydrogen. And the capex, the investment is not so high that in the case of hydrogen. So there are systems that you are coming, maybe electromechanical systems that can facilitate other alternative for storage energy. That is true.
And hydrogen is more dangerous than air, which is a very important point too. Yes. Well,
Sorry. Do you want to ask us? So I think it's answering your questions. We think in all technologies. For example, hydrogen. If I put in my house a storage, I will use batteries, no hydrogen, for safety. if you are using, for example, for electrical car, you can use batteries, supercapacitors. So you are thinking in plane, ship, you can move to hydrogen. It's at Miguel's side, it's very important, for example, for the companies, is the economic business questions. For example, Iberdrola is an electrical company. They are interested in using electricity to produce hydrogen. And the hydrogen move to, for example, for ammonium to have in Celtiberia. Repsol is the contrary. They use hydrogen in order to prepare new compound with low carbon content. So if you speak about Iberdrola, they say electricity is the best. Wind is the best. If you speak with Repsol, say the contrary. What is the interest of this company? So we have to pay attention. In the scientists, we have to pay attention and to put questions, like I said before. What is happening with the gigafactories? How many gigafactories? We have a lot of in the roadmap. There are a lot of investment in money with this next generation. You imagine a company, for example, you have a company, a gigafactory, you have 40 million euros, and this gigafactory is stopped, doesn't move. What is happening? Who is the responsible of this money? This is the problem. At the scientists, at the university, at the academics, and we have to say the thing that we consider more important from the scientific point of view. But this is, as Michelle says, is business is business.
I think.
To make no, the piezo, no. No, let me just a short comment, if I can. He say hydrogen is dangerous. Maybe it's dangerous to get installation at home, okay? But for example, some trucks, some heavy duty transportation, it is not possible with batteries. And then the only solution is hydrogen. For example, in Barcelona, we have a station of hydrogen that is from Iberdrola. Iberdrola is producing hydrogen that is supplied to, I don't remember, but because now they buy more buses, I believe that with the new buy, the total will be more than 30 buses just using hydrogen. The only question is the cost of the hydrogen. The cost of the hydrogen. If you can reduce the cost of hydrogen, and that depends of the cost of the electricity, because essentially you are using 50 kilowatts hour to produce 1 kilo of hydrogen. So 70–80% of the cost of hydrogen is the electricity that you are consuming. So if you have very cheap electricity, hydrogen is very cheap and is a solution.
Okay, I think, President, if you have any more questions. No. Okay, so I think that we should make the closing 2 words at least to say that has been a very exciting day. Thank you very much to all the participants. Marisol wants to close the session herself, and I have prepared 2–3 words, but I'm not going to tell them, okay? Just to depend that we have very extrinsic factors that we make roadmaps and so on, and afterwards happens things that we don't expect to happen. Thank you very much. Please, Marisol.
Okay, so thank you, all of you, for staying here till this very late, and thank you for all the speakers. And just to say that right now there is no winner technology that is going to save the world, but we have to explore all of them, and we have to try to get the best of all of them, including piezoelectricity. So, thank you so much.